Hey everyone. All right, I'm going to try this again. I've been making this video literally all night, uh, but I think I restarted everything and now it should work. So we're going to talk about periodic trends. You may hear my puppy Loki in the background, so I apologize in advance, although he's really cute, so I guess it's fine. All right, so we're going to talk about how atomic radius, ionization energy, and electronegativity of an element are related to its electron configuration. Now, I know not all of you have done electron configurations yet, and that's fine. We're going to, for those of you who weren't able to do them today because I had to leave, we will be doing them probably Thursday, so we'll all be caught up. So the first trend is atomic radius. And that is the distance from the nucleus to the outermost electron shell. So just like in math, how if you have a circle, the radius is from the center to the outermost edge. In an atom, you've got your tiny little nucleus in the center, and then you have these energy levels around the outside. And your radius is from that nucleus in the center to the outermost energy level. And that's where most of our volume is those electron energy levels. So I can't have this show them so that I click one at a time, so you can just see all the answers to my questions, and that's fine. So if we look at Bohr models going down the first column of the periodic table, we see that hydrogen only has an n equals 1. So if you haven't done electron configurations yet, that's okay. You have done Bohr models, I'm sure. And so if you've only got one electron, you've only got one ring. And then you learned you could only put 2 in that first ring. So when we get to lithium and we've got 3, we've got another ring. We have to add another ring to the outside where this electron goes. And for sodium, we have 11. So we do our 2 and our 8, and then one more in this outer ring. So as we go down, we have the same number of valence electrons, but we're increasing the number of rings each time. Right? So as we go down, as we're adding rings, we're getting bigger and bigger. And that's our radius is getting larger. More electron energy levels, bigger radius. Going sideways, if we go across the row that starts with lithium, you'll see they did not include the first ring, n equals 1. These all would have 2 electrons and then n equals 1. We're looking at n equals 2. And as you go across, we're adding electrons, but those electrons are going in the same energy level. We're not adding additional energy levels around the outside. But what else is changing is we're adding protons into the nucleus. And so what's holding those electrons around the outside of the atom is the attraction between the positive charge in the nucleus and the negative charge of those electrons around the outside. So if we go across and we add more and more protons into that nucleus, it's kind of like producing a stronger and stronger magnet on the inside where those rings are getting pulled closer and closer and closer together. So when we've got more protons, we have a stronger force of attraction. And when we have a stronger force of attraction, our atomic radius gets smaller. So if you have your periodic table, you can draw these arrows right on. Atomic radius increases as we go from right to left, and it increases as we go down. So if you don't already have the periodic table, if you are still fully online, I put a blank periodic table, the front and the back of what I gave everyone in class, on Schoology in the orange information folder. And then eventually, if you are in class, you'll get a cardstock one. But you can print this one out front and back and have the same thing everybody else does. So this formula, Coulomb's law, it's pretty important, but it's not a formula we're going to do anything with mathematically. Oh, here's Loki to say hi. Hi, Loki. Oh, and now Luna's coming to say hi too. So this formula, we're not going to do any calculations with it, but it gives us the relationship between the force of attraction and the charge and atomic radius, and it just gives us kind of an idea about how they affect each other. So if we increase the charge by, say, adding more protons into the nucleus and making that a stronger force of attraction, it causes the force of attraction to get bigger. If the atomic radius gets larger, and that distance between the positive charge and the negative charge gets larger, then our force of attraction is going to get smaller. Right? I can't click enter. All right, so ionization energy is the next trend we're going to look at, and it's the energy needed to remove an atom's outermost electron. So in the case of sodium here, the easiest to remove electron would be the one that is farthest away, right? So the ionization energy would be the energy it takes to remove that electron from this sodium atom. So when we have a greater attraction and that electron is being held tighter, we have a greater ionization energy. If we increase the radius, we decrease the force of attraction, just like from that Coulomb's law thing, and that means that it's going to be easier to take an electron off. Larger radius, easier to take an electron off. It takes less energy to take that electron off. Right? So it's the exact opposite trend of atomic radius. It increases as the radius gets smaller. So you can write that on your periodic table also. Those arrows go in exactly the opposite direction as the atomic radius ones. And the last trend is electronegativity, which is an atom's ability to attract electrons in a chemical bond. A larger ionization energy also means a larger electronegativity. So if an element or an atom really wants to hold on to its electrons, then it is also likely to really want to take electrons from other atoms. So it follows the same trend as ionization energy. The only difference is that the noble gases, the ones on the very end that start with helium, those have no electronegativity at all. They do very much want to hang on to their electrons. So their ionization energy is very strong, but they're happy with the electrons they have. They have no interest in taking anyone else's. So their electronegativity is 0. So you can write those trends right on your periodic table as well. They follow the same direction as ionization energy, except for this last column here, where the electronegativity for all of them is 0. The last thing we're going to do is watch a couple of videos. I will show you these demonstrations from video 1 in class next time we have the opportunity to, or sometime before fall break. This first one shows us the reactivity of the group 1 elements, lithium, sodium, and potassium. So elements with a very high electronegativity, meaning they very much want to take electrons, or with a very low electronegativity, meaning that they want electrons so little that they're willing to give their own away, can be very, very reactive. They're very motivated to either take electrons or give up electrons. So let's see if we can make this work. Apparently not as easily as I thought we could. Oh, but here's the video. Let's move this over. All right.
Here I'm working with some lithium metal, very difficult to cut. I've got a piece of sodium here, pretty easy to cut. You notice when I cut through that the fresh sodium is very shiny compared to the rest. Let's zoom in real quick. Let's see if we can really get in there. So this side will reflect a lot of light. The other sides are pretty dull. And you'll see that especially with the potassium here. I'm going to go ahead and give this kind of a half cut. So for the potassium, this is the side that's freshly cut, and you can see the dullness to the other sides compared to that one. So I'm going to go ahead and take those 3 and I'm going to add them to water, and we can look at the kind of reactivity of those 3 alkali metals with water. So here I'm going to take the lithium and add that to the water. It's going to generate hydrogen gas and lithium hydroxide. So you're going to see a pink color develop here, and then you're going to see some smoke come off, and that's either lithium metal or that's lithium hydroxide coming off of there. Maybe a little bit of liquid water. but it's not as reactive as, say, sodium, so I'm going to put sodium into the next one. And the sodium is actually probably going to ignite. So you'll see some orange flame, perhaps, or some sparks, or some shrapnel. And then the last one, I'm going to go ahead and put my 2 pieces of potassium in that I've cut in half. So this is less potassium than the other two in terms of amount. You'll find that the reactivity is a little bit greater.
All right, so we'll talk about, first of all, why those turned pink in class. And also, I will show you this demonstration so you can see these metals catch on fire with your own eyes and water. But you'll notice that as we went from lithium, which was at the top of the periodic table, down to sodium and then potassium, they got more and more reactive, right? We saw that lithium react very quickly, the potassium react very quickly. And that's because its electronegativity is very low. Now let's watch on the other end of the periodic table, up by fluorine, which is the most electronegative element on the periodic table. So we're going to watch those halogens on that end. The sound on this is kind of weird, like it's non-existent and then suddenly it's there. And these are halogens reacting with aluminum powder.
Actually remove this.
So the guy in the video is clearly talking, but I've never heard what he says, despite the fact that every year I use this video. Bromine is one of only 2 elements on the periodic table that is a liquid, so he just put aluminum foil into liquid bromine. These we will not do in class because these elements can kill you. Not sure the purpose of the music just on that part, but do not blink when he puts this aluminum into the fluorine. All right, so as you can see, exactly the opposite trend for this. As we go up the periodic table towards elements that are more electronegative, they become more reactive. So this is periodic trends in a nutshell. Tomorrow you will have an assignment on comparing. It will be pretty simple, where you're going to say which one has the greater electronegativity, which one has the greater ionization energy. All asynchronous assignments are now due Monday at midnight. So if you're in class and you get a piece of paper, it's due in class Monday or Tuesday. If you're doing it online, it's due Monday by midnight. So I will see you all again soon. Have a great day.